Okay, so we'll start now with the next topic, that is called as plain sedimentation. So first we'll understand what is sedimentation, and then, as we have seen in the initial classes, that this sedimentation is divided into three main types. That is, first is plain, then sedimentation aided with coagulation, and clariflocculator. So this we'll see separately. So before starting the concepts from the sedimentation, we will see one practical case and try to understand what is the exact meaning of sedimentation. Okay, so start visualizing there is a jar. Okay, this is a big jar. In this jar there is water present up to this level. Okay, so the water is present in this jar. Now few information I am giving, so you write it down or you just pay attention to this. This height of water I know. The height of water in this jar is h. Now for experimenting, what I am doing is I am taking two stones. So I am taking now two stones. So one stone is smaller in size and the second stone is larger in size. So this is stone 1 and this is stone 2. Now let's say I am dropping this stone at this surface very gently. Okay, I am not applying any force, I am not throwing it inside, I am just gently releasing the stone in the water. So my first question to you is, you have to start thinking. Okay, so then only you will better understand the concept. The first question is, which of these stones will first be present, or we can say which of the stones will first reach the bottom surface of the jar? Will it be stone number 1 or stone number 2? The second question is, can we calculate the time in which the stone will reach this bottom surface? That is, what is the time taken by the individual stone to reach this surface? So first we'll answer the first question, which will reach first. Okay, so which will reach here? So among the first and stone number 1 and stone number 2, as the weight of stone number 2 is greater, so this will come faster, or we can say this will reach quickly to this surface. So which will come first? Stone number 2. Now can we calculate the time? Okay, before calculating the time, first we have to calculate with what velocity this particle is coming down. I hope you are getting it. There are two stones we have taken. The first stone is smaller stone, second stone is larger stone. As the larger stone weight is more, that's why under the action of gravity the larger stone will reach this bottom surface first. Okay, it will reach quickly with respect to the first one. Now as it is reaching quickly, that means the velocity with which it is reaching, that velocity is also more. If the velocity of this particle is vs1 and this is vs2, then we can say vs2 is greater than vs1. Okay, now this vs1, okay, this vs1 or vs2 or this vs, it is called as terminal settling velocity. Okay, terminal setting velocity. And this process in which a particle reaches the bottom of the surface, this process is called as sedimentation process. Okay, now just compare these two particles with the suspended impurities which are present in water. Let's say if we introduce the water to a tank like this and we keep it for some time, then what will happen? Whatever the suspended impurities are there, they will slowly reach this bottom of the surface. So one by one, all the particles will start forming the bottom sludge in the tank. So this process is called as sedimentation. Okay. Now in this process, as I have told you, the one thing that we require is with what velocity these particles are going to reach this bottom surface. So this is the first question. Now, once we get the velocity, can we calculate the time? Yes, we can calculate the time also. So we know that distance is equal to velocity or speed into time. So this time is equal to distance divided by velocity. So time is equal to distance divided by velocity. Now what is the distance this particle is traveling? So we are taking the example of 2. Okay. So it is traveling h distance. So the distance is h. That is height of the tank, water in tank. And what is the velocity with which it is coming down? It is coming by the velocity vs2. So the second particle will take the time h by vs2. So with this now we can even calculate the time with which or how much time that particle will take to settle at the bottom of the tank. Now for calculation of this terminal velocity, there is one formula which is given, and that formula is given by Stokes law. So Stokes gave the formula for calculating Vs, and this is called as Stokes law. Okay, so for what Stokes law is used? It is used to calculate terminal settling velocity. So write down Vs square is equal to 4 by 3 times of g in bracket rho p minus rho w into d divided by cd into rho w. So this is the main formula which is given by Stokes. So this is applicable for any flow condition and for any medium. That is, this is an universal equation. Okay. Now based upon the type of flow, this equation is modified, and there is one thing only that is going to change in this equation, and that is this CD value. So initially we will write all these terms which are present here, or else first we will finish it the other equation. Okay, so this, write down these three cases. So in case 1, if a Reynolds number Re is less than 1, so that means the flow is laminar flow. So for laminar flow, the value of CD is 24 by Re. So you just have to substitute this 24 by Re in this equation if the flow is laminar. Second, if Reynolds number is between 1 to 10 to the power 4, then this flow is transition flow. And for transition flow, CD is equal to 24 by Re plus 3 by root Re plus 0.34. And if Reynolds number is greater than 10 to the power 4, then it is called as turbulent flow, and for this CD value is 0.4. See, now based on the Reynolds number value, you have to substitute this CD value in the above equation and get the value of settling velocity. Now here other terms, or what we can say, we'll write the meaning of each and every term starting from Vs. So Vs means settling velocity. Okay, then this G stands for acceleration due to gravity. What is the value for G? 9.81. Then this rho p and rho w. So this rho p stands for mass density of particle. Mass density of particle. Then rho w is mass density of water. This d stands for diameter of particle. Okay, and CD value I have given it here. This Re stands for Reynolds number. And the formula for Re is rho Vd by mu. Okay, rho Vd by mu. So substituting this all formulas, we'll get the value of settling velocity. So here rho is mass density, V is velocity, D is the diameter, and this mu is called as dynamic viscosity. So you can see that the settling depends on the viscosity of the liquid also. So these are all the terms which are present. Now this settling velocity we have to use in plane sedimentation only for the laminar flow condition. We'll be taking the laminar flow condition. So settling velocity for laminar flow condition. So for laminar flow condition, what is the value of CD? 24 by Re. So if you substitute that 24 by Re in that equation, you will get Vs is equal to G into rho p minus rho w into d square by 18 mu. So this is the most important formula that you will have to remember throughout this chapter to calculate the settling velocity. So these all terms we have already discussed in this previous page, so you can refer it. There is one more upgradation to this formula, that is if we divide this equation by rho w, then we can get it Vs is equal to G into this rho p divided by rho w. So rho p divided by rho w is nothing but specific gravity. Rho w divided by rho w will be equal to 1 into d square divided by 18, and this mu divided by rho w will give us the value which is called as kinematic viscosity, and that is represented by nu. So you can remember the first formula only, this is enough. But sometimes in exam, instead of dynamic viscosity, kinematic viscosity is given, so you can directly use this second formula. So here one unknown term is this mu, so this mu is called as kinematic viscosity, kinematic viscosity, and the formula for this is dynamic viscosity divided by density of water. So these are all the formulas of settling velocity. Now with this all the formulas, we have to move to the next main important part, that is understanding the plane sedimentation tank. Okay, so we have seen, we'll quickly revise what we have seen. We have seen what is the meaning of settling of particles. We have understood which particle will settle first. The particle which is having more weight, that will initially come down to the bottom of the container. Okay, now if you just see here, then this is the diameter of this particle and this is the diameter of first particle. Now from our analysis we have said that this vs2 is greater than vs1. Okay, as the weight is more, it will reach faster. As it is reaching faster, that means velocity of this second particle is more. This we have seen directly. Now if you see the equation, if you see the equation of this velocity, settling velocity, you can see this settling velocity is proportional to square of diameter of the particle. That means if there is a smaller particle and bigger particle, which settling velocity will be more? Whose diameter is more? So here in this case, this second diameter is greater as compared to first. That means the settling velocity of the second particle will be more. So this shows the direct relationship between diameter of particle and the settling velocity. Okay, so remaining things we'll see in the next video.